improvements we made, I think we'll find very interesting. Certainly made an impression on some of the earlier groups, some people in the earlier groups today, and we appreciate you taking the time to attend this webinar. In the afternoon, it's always a tricky thing because you've had lunch, you're listening to a terrific monotone voice like mine, and the tendency is to put you to sleep. I'm going to try not to do that here. We'll try to keep it interesting and at a pace that that allows you to stay involved and to pick something up here. This is a slightly more technical presentation than some of the others because we're not really so much promoting some new commission program or new sales program per se, but giving you some added tools to be able to get out there and sell and promote the VLED optical systems and to see how the improvements we've made have really not just kept us abreast of the industry, but we hope you'll find by the end of this presentation that we're actually out there leading it, that you'll find that we're ahead of the curve. So without further ado here, we'll go ahead and get right into the session. There's still a few more people that are signing on. We're glad to see that. A good number of them came up, and in any event, we'll get right started with this. The improvements that we've made with the new VLED system relate not so much to just things that were, it wasn't things that were necessarily errors or mistakes in the first one, but it's improvements that have come along because of advancements in the technology and things that we've learned along the way. We'll get right into showing you what the differences are. The advancements that we've made from the old versus the new VLED modules are fairly substantial. In most cases, when you look at the individual distribution types, we're seeing anywhere from a 40 to 45% increase in the amount of light output that we're getting from these. Now, we don't want to make a big deal about lumen values because though those are the core of what we end up using as far as illumination is concerned, we need to stress this point over and over again that we do not sell the VLED modules based on a lumen comparison to someone else's modules or someone else's system, because placement of that light, not the amount of light, is the important thing here. However, we need a certain amount to start with, and as you notice here in all of the systems, we've got a substantial increase in the lumen values that we're getting out of the luminaire. And one of the other significant advancements is in the luminaire efficiency rating. From the high 30s and low 40s, and in some cases flirting with 50 in some of the smaller modules. This is all based on the 120 LED version, which is the least efficacious of all of the modules. You can see that we're up to right around 60 lumens per watt in all of our modules now. And that is a lensed enclosed system, so that's a substantial gain. And in addition to it, because of some advancements that LumaLEDs has made with the Rebel, using the new Rebel ES LED, not only are we getting 25 to 30 more lumens per LED out to start with, we're doing it with a lower wattage draw or lower consumption of power. And that's an important point because, as we're going to find out here in a few minutes, power consumption equals heat, and heat equals degradation of light output. And so all of this rolls together in order to make a far more robust and very, very well-performing LED system. Now, the first thing we want to do is I've had a few phone calls that have come in when we sent out the ITL reports, and these are all LM79 protocol testing. When we sent these out just a few weeks ago, because of some changes that were noticed on them, we're using the Type 2 here in particular to note it. You'll note that where the cursor is right now, it calls out that it's a 120 LED neutral white Type 2 module. We'll go ahead and inflate this just a little bit because the IES classification on this module now reads as a semi-cutoff Type 3. And some people have said, well, what exactly is going on here? First of all, we need to make sure that everyone understands that when we're comparing LED systems or looking at LED systems, we can no longer use the old full cutoff, semi-cutoff type of rating system. Now, the ITL reports still have that core in them. It's part of the function of the ITL reporting, and so it shows up on all the reports that go through their system. It's in the actual computer programming. But the thing to pay attention to here are the bug ratings, the backlight, uplight, glare ratings, and the reason for that is that cutoff, semi-cutoff ratings as a reference to HID product is based on a comparison of light levels to the overall lamp lumens, whereas LEDs compare light levels to the luminaire lumens. And that is a significant difference. You usually have about a 30% reduction in luminaire output from any HID fixture. And so that's one of the reasons why the semi-cutoff and cutoff designations are no longer valid for LEDs. We have a technical report that was published by lighting analysts who make the AGI 32 program that explains this in a very, very concise single-page fashion. Please feel free to email us at the end of this program requesting it. If you'd like to get a copy of that, we'll make that report available. And it explains the difference between HID and LED in general. It applies to everyone when it comes to the cutoff versus the bug ratings that are out there now, or the LCS graphs. The other has to do with the rating of type 2 versus type 3. Now, all of the typing that we do when we develop our optical systems is based on application distributions, not definition of distributions. And what we mean is this. When you look at this chart on here, you see a few things. First of all, the line here that we've shaded in pink is actually the line that designates where the type 3 pattern would begin. Anything that touches that line or extends forward from the curb line beyond that dotted line that's shaded in pink then would classify as a type 3. Now, what is it that we look for to touch that line? Well, this island area that you see here, this dotted line kind of egg-shaped surrounding this X, represents the area that is up to 50% of the maximum candela. The X is the max candela point. Everything in that line and inward is at 50%. Wherever that 50% trace falls designates the distribution type of the optical system. And if you notice, we just touched that type 3 line there, and that's the reason why this classifies as a type 3. However, in application, this is a type 2 distribution, and this is a fairly common issue that comes up with optical systems out in the field for many manufacturers. You sometimes will see a type 4 distribution or a type 4 classification on a type 3 fixture or even a type 5. Don't let that throw you off. The manufacturer is giving you the proper guidance as far as how it functions, and that's what we wanted to show you here. So honesty in reporting is an important thing. When we look at the old system versus the new, the question is, are we really doing better? Well, yes, we are. What we're showing you in the yellow and the purple ISO foot candle lines here is the comparison between the old in yellow and the new in purple 0.5 and 0.25 ISO foot candle lines. In addition to having a pattern that is slightly larger because of this increased output that we have, we also have an increase in maximum foot candles that the systems put out. In these configurations, at the 20-foot mounting heights that they're run at, the old system would have been 2.3 foot candles. The new system is at 4.4. Now, that's not a large amount of foot candles directly below the pole, but what it does do is when you're doing comparisons with HID systems and the average foot candle ratings come into play, and some of your specifiers do still pay a lot of attention to that, this will help that number look a little more in line with what they're used to seeing, although it won't impact substantially your uniformity at all. We'll see a little more on that here in just a moment. To illustrate how much improvement there is in the old systems versus the new, do a little bit of a roadway comparison here. What you're looking at are two layouts that are done using a total of 4 fixtures. We've isolated on 2 fixtures in the center, 2 assemblies in the center. And we're showing a spacing of 120 feet along the curb line. The poles are at a 20-foot mounting height. These tick marks that you see are at 40 feet on both charts. The red line is the ISO foot candle line for 0.2 foot candles. Green is 0.5, and the blue is the 1 foot candle line. You'll notice that in the old system, the 1 foot candle lines were basically islands, whereas in the new one they merged together with the same spacing, indicating we're getting a little more extension there of the pattern. And between the luminaires, right in the center of the chart, you'll notice that in the old system, we were barely getting out there with a half-foot candle line, just trying to flirt with 30 feet, whereas we're getting a little bit beyond it here in the one on the right-hand side. An even more stunning example is when we want to go for a 1 foot candle rating on these on these assemblies. Here we've taken the same type 2 distribution. We're putting them at 110 foot spacing and a 20 foot mounting height. We've changed the scale now to being a 30-foot scale just to get a little more detail to it. You'll notice that by moving the fixtures in just 10 feet, what we've now been able to accomplish is a very even and smooth, on the right-hand chart, 1 foot candle line approximately 28.5 feet out in front of the luminaire. This is important because if you look at a typical roadway application where you want to illuminate a 30-foot wide roadway to a half a foot candle, you can see here that we do that quite well. In fact, we nearly make 1 foot candle on that roadway. Now this again is using 120 LEDs mounted at 20 feet and spaced 110 feet apart. This is fairly substantial performance, and you could not get this type of system out of a 250 watt metal halide simply because the foot candles you would have directly below the pole would completely throw your uniformity off. So this really illustrates some of the major advancements that we've been able to accomplish within this new system. Well, let's review what it is we're doing with the VLED system that allows us to hit some of these performance levels. First of all, we're taking each individual LED and controlling it with 3 different types of reflector prisms, and we call them reflector prisms because one half of the unit operates as a reflector, the other half as a prism. We then combine these in an optical system with one set of prisms operating from 0 to 50 degrees, one operating roughly from 50 to 65, and the other from 65 to 72 degrees, and then array them much as you would a sports floodlighting system so that we create our various distribution types. Now, one of the significant improvements that has taken place in the system is that, again, as we mentioned early on, the new LumaLED's Rebel ES, for the same amount of power, same amount of forward voltage, no extra consumption at all, is now producing 130 lumens where before it had been producing 105. So that 25% increase is a big part of the gain that we see. But there's more to come here, as we'll see in a moment. In discussing, as we had when we introduced the VLED system, how these prisms work, you'll notice all 3 have the same upper arrangement, or upper component. And that upper component is a collimator. The collimator takes the output of the LED and either directly in the very front of it or in directing it through the sides, takes the output of the LED and redirects it so that everything coming out of the collimator is a coherent beam going into the prism below. You want all these lines coming out of the top half here, the reflector portion, to be parallel. And that way, the prism below then redirects that light output into the area that we can then use it and aim it in order to create our overall pattern. This particular prism is the prism that's used for the 65 to 72 degree range, the high angle units, has approximately, this with its concave front, about a 12 to 15 degree beam spread, and we have more of these than any other prism in the system because that's what's developing our minimum foot candle levels out in the pattern. Now, this is another area of improvement has been in these prisms. The reason why is very simple. The initial tests that were done, the ITL reports that were done for the VLED system, were done within the first, let's say, 1,000 to 2,000 components that we had run off of the tooling. And for anyone who's ever been in the manufacturing process, understands that either in injection molding or, interestingly enough, in die casting, but particularly in injection molding where you're using plastics or an optical material, once you break the tool in, the tool essentially polishes itself, and from that point forward you have a very, very nice finish to the product. It actually becomes more optically clear once the tool is broken in, and because of this, just by testing again after, say, 5 to 10,000 units, we now have components that are producing about 5 to 7% or are optically clear enough now to produce about 5 to 7% increase in the light level of illumination passing through them. So this is another area where we've had an improvement, is in the manufacture of these particular components. And as we mentioned before, we take the prisms, we then array them to where there's no backlight coming off of the luminaire, or we don't design any into it, and we use one set of prisms for the 0 to 50 degree range, another for the 50 to 65 degree range, and the other for the 65 to 72 degree range. And then we take those patterns, combine them all together to give us a type 2, 3, 4, 5 pattern as a composite beam overall. What that means is that we can control the light level at any point within there, either close in or far out from the pole, which allows us to have very good uniformity. One of the things that's been noticed here over the life of the VLED system is that it is more visually comfortable than other units out there. And we can debate whether or not LED systems are visually comfortable at all, but it's been proven in the field that the VLED system is more visually comfortable, and there's a specific reason for that. In the design of the components and the design of the system, it's geared around visual comfort. Here's how. When you look at an LED, and certainly this is a much blown up version of it, the LED itself, the only light portion is coming off of what's behind this bubble. And you imagine 130 lumens coming out of that point is a fairly intense amount of light. A raw LED is one of the harshest type of light sources to look into. It's like looking into the arc tube of an HID lamp or the filament of an incandescent or a halogen lamp. You just don't want to do it. That doesn't make sense. Very, very small too. If you look at the size of the Rebel ES here on a circuit board as compared to various other elements we know the size of, it's a tiny piece. What we do is we take that LED, which is approximately 1/8 of an inch across, thereabouts, and when we locate it inside of the recess in the columnator on the top portion of all of these reflector prisms, the columnator then spreads that pattern out to make it approximately 5 or 6 times the original diameter. We haven't increased the lumens at all coming from the LED, so this function alone mitigates the harsh brightness that comes from the raw component. Now what you're looking at here in this photograph is a photograph of a Type 4 optical system without anything turned on. We're looking into the prisms, and you see this is a back row of the prisms here. This is the side of it over here. You're actually looking into it as if you were where the pattern is being thrown to. And you notice the little distortion, the little circle in the middle of the yellow disc there. That's that little recess where the LED is. The entire yellow portion or yellow image that you're seeing is the full LED. And you notice how it fills that prism up? That's what it does to the light. So that little dot that you saw is now filling that entire prism. And that's one of the ways that it helps to mitigate the brightness. And as we rotate this optical system 90 degrees, you can see how the images that are now in yellow shift to some different prisms. That's the other way we mitigate the brightness, is that you don't see all of the LEDs at one time. You only see a certain number of them where you're looking into the main beam. And that's what happens with a typical HID system. Provided that you're not looking at the filament, the only main beam that you're really going to be hit with, or the only beam you're going to be hit with, are the facets that are directed towards you. As you move, you see light coming from different facets, much the same as happens here. So when we take that output from the LED, run it through the collimator, create the coherent beam, and then have the coherent lines coming out the front, we can keep that light from striking someone in the eyes, just like you can stand next to a 1,000-watt floodlight that's a spot, and if you don't look into the arc tube, the beam will go right past you. But if you move in the main beam, it'll become very bright. The key element here is that we're taking and spreading the beam over a larger surface. So if you rotate that prism 90 degrees to you, so now you're looking into the concave surface, you can see that the LED being put into the recess up above gets considerably inflated down in the prism below. And so we reduce the edginess or brightness of the individual LEDs, the raw LEDs, by using these prism reflectors. And it's the intrinsic nature of that prism to spread the point source over a larger area, and that mitigates the hot spot. One of the other things that comes into play is how we array them in a system. Now, by looking at other systems and what happens visually, you'll be able to appreciate another factor that helps give us the visual comfort in the VLED systems. One of the most popular types of systems out there is what's known as the light bar system. And the concept behind the light bar system is that essentially we take an LED, we put a lens over it that imparts a pattern to it, and we repeat that over and over again for however many LEDs there are. If there's 60, 120, 180, it doesn't matter. What we end up with is one large pattern based on whatever the small pattern is we start with because of the additive properties of light. Now, two things come into play here. One, we can't control, or you can't control the difference in light levels that are in the center of that pattern versus the edges. Whatever is designed into that lens is what it is. The other factor that comes into play is that whatever the output is of a single LED, if that output is visible to the human eye, to the viewer, every other LED in that system, because it has the same pattern, will have the exact same thing happen. You will be able to see each one of those LEDs. And though the lens over one LED mitigates the brightness of it to some degree, you're looking into all of those LEDs, and that's one of the things, a major factor that contributes to the harsh brightness that you see in a typical light bar system. Well, not all systems are light bar systems. Some of them use some type of reflector control, if you will, that blocks the view, or that limits the view of the LED. And indeed, those systems can be arrayed to produce your asymmetric patterns or type 5 patterns. You won't have necessarily the view of each individual component, and that's a good thing. However, for the other components, you do have a direct view of the LED. And in these instances, these would be more along the lines of what are known as reflector-based systems. What you have is a reflector controlling the output of the LED, and you're looking into the raw LED itself, that little point source without any mitigation to it. And these are extremely harsh and glary as well. For that very reason, is because of the harsh brightness that a raw LED has. Either of these systems have drawbacks in this regard. The reflector-only system, one type, reduces the number of LEDs that are viewed from any angle, but allows you to see the raw LED in its harsh edginess, or its harsh brightness. And then the other type of system, the light bar system, allows all the LEDs to be seen from nearly all angles with a little bit of reduction of the on-angle brightness because of the way it spreads the beam out, but you're still seeing each individual LED in that system. And that's the drawbacks that it has as far as visual comfort is concerned. The other system that's out there is also a prism system similar to ours, but with one major difference. In the VLED system, aside from using 3 prisms, we start with the collimator at top, which results in a coherent outgoing beam. If instead we remove that collimator and go with a defocused image into the top of the prism, we have more random angles of light exiting the prism, and as a result, those random angles create glare in off angles that aren't doing anything to enhance the pattern. And it's not as controlled, and so that's the reason why we have brightness there. It would be much the same as taking a sealed beam lamp that you don't see any brightness from and removing the cap over the filament, and now that filament brightness is striking you in the eyes. So all of these elements combine together to make the VLED system the most visually comfortable system out there on the marketplace today. The fact that we're controlling the raw LED and not allowing you to see it, turning it into a coherent beam, and reducing the edginess or brightness of it, spreading out over a larger surface, and putting the image in there, or putting the lights in a particular location, a particular portion of the pattern, all contribute to that visual comfort. In designing our optical systems, the VLED optical systems, we're going to make a real trite comment here. We design for quality of illumination. You like that statement there? What exactly does that mean, designing for quality of illumination? Well, everybody would like to think they do it, but most people design for cost of illumination. It's not what we're doing here. First primary source, we're looking for quality. That means that we, as we discussed, we're producing a system that has tremendous visual comfort by comparison to others. We also design our systems with an emphasis on uniformity, not just light output. And we're looking to illuminate to acceptable and familiar practices. We're not asking you to go out there in the field and make excuses for our optical systems by saying, well, the LEDs do things different than HID, so what you think you're seeing, you're not really seeing. There's really more light there, even though it doesn't look like there's more light. Or getting into these discussions about scotopic and photopic photometrics on optics and all of that. We're not going to go there. We're going to do this in a much more reasonable fashion, and include color and color temperature of the LEDs to acceptable practices that have to do with quality of illumination, not just looking for quantity. Let's start with the discussion of uniformity and what we talked about before, average foot candles, which essentially all comes down to one thing, lumen output of the luminaire. This field of analysis is a 5-foot candle average. I've got 5-foot candles at every measuring point on the surface, 1-to-1 average to min and 1-to-1 max to min uniformity. This also is a 5-foot candle average. Probably numbers we would be more familiar with. We've got a maximum of 13 with a minimum of 3 with some acceptable levels in between, a max to min level of 4-to-1, average to min of about 1.5-to-1, 1.67-to-1. This is getting a little more outside the range of acceptability. We have here another 5-foot candle average. Our max is 21-to-1 because of 21-foot candles in the center versus 1-foot candles around the perimeter. And now we're going to go from the sublime to the absurd. This is also a 5-foot candle average, where we're focusing all of our output into the center of the field with no light anywhere else. Do you get the point? Average foot candles don't mean anything. Without uniformity, they're not telling us anything. Lumens don't mean anything. Unless we know where the light is going, it doesn't tell us anything either. Excuse me. And that's the important feature or fact to remember when it comes to the design of the VLED optical systems or the engineering of the VLED optical systems. Our primary target parameters are foot candle placement and uniformity, not lumens. So that begs the question then, how did we come up with the foot candle levels that the system puts out? Very simple. It's called reverse engineering. Why reinvent the wheel? We know what people want. People want to do exactly what they've been doing for years with their HID systems. So we took the footprints from the 250-watt metal halide systems of the most acceptable specification-oriented fixtures on the market. No need to discuss who they are necessarily, but we looked at 4 different fixtures from 3 different manufacturers and designed the systems to the 0.2 and the 0.5 ISO foot candle lines, and then backfilled the rest of the pattern for acceptable uniformity. We didn't just accept the uniformity the lamp was giving us, we designed into it uniformity based on where we put the illumination levels because of using this prism design. So the key here is to equal the perimeter foot candle levels produced by HID lamps, not the lumen output of the fixture, and then to backfill the rest of the system. Here's the result. Many of you saw this or may remember this from the very first presentation we did. This is comparing the Type 3 with the 0.5 ISO foot candle line, the yellow being the HID system, the purple being the VLED system. And when you first look at it here, you look at it and say, well, that HID system's kind of better. Fact, though, is that whatever is behind this heavy white line is not applicable because that's on the house side. We don't want that much light back there. What we really want is the light that's going to the sides. You notice all the systems pretty much reach the same levels towards the front with some irregularities. But when we look at the spacing of the next luminaire to the sides, we're virtually the same when it comes to the 2 outer units. And in the center unit, with some irregularities, it's about a half a mounting height spacing difference. If I then go to the 1/4 foot candle line, which gives me a half a foot candle between fixtures, my differences are for all intents and purposes gone. And what I'm doing is I'm able to use essentially a 120 LED system to replace a 250 watt metal halide lamp. Stating it in other terms, I'm taking and using 135 system watts to replace 275 system watts, saving that energy but having very, very good placement of light. And when you look at the foot candle levels, with a 4-foot candle maximum from the LED system as opposed to 6 or 8 or 7, which is going to blow our uniformity ratings on here, a much more acceptable quality of illumination coming from the LED system. The other element to consider here has to do with color. Now, when we've been looking at metal halide out in the field for all these years, most of the systems are running around 4,000 K. Some are at 3,200, some are at 3,000, but most of them are running around 4,000 K. The game that's been played, though, with LEDs is to run them up to around 5,500 to 6,500 because the higher color temperatures tend to allow more lumen output, and that's all the other manufacturers are looking for is quantity of light and not quality. That's not what we're doing. But there is a definite difference and improvement with LEDs. What we're doing here is we're taking 2 charts. It's the same chart, actually, for a metal halide, 4,000 K metal halide lamp. We've arranged them like this so we can take an LED that's a 4,100 K color temperature LED. That's the color temperature of moonlight. That's why it's so acceptable in the market, the neutral white LED. and we've compared the amplitude on the x-axis, or the y-axis, which is the chart on the left, and the wavelength from 400 to 750 nanometers, essentially, across on the x-axis. And we're looking at where the light levels fall within the metal halide versus the LED lamp. Now, you notice the metal halide lamp, the color is very spiky. To the eye, it appears white, but the fact is that it doesn't have a lot of color content by comparison to the LED. And particularly when we get down into the amber and the red zones, we see that the LED has a lot more of this color content, which warms up the look of the overall environment. Now, the more color content there is in the light source, the better the visual acuity in the field that's illuminated. A very simple way to compare this and to prove this, without ever touching LEDs or any other discussion, is look at a project that has been illuminated in the past, the 5-foot candles of low-pressure sodium versus 5-foot candles of high-pressure sodium versus 5-foot candles of metal halide. Which ones look brighter? Well, obviously the HPS and metal halide do. The reason why is because you have more color content in those fields of illumination. It's exactly the same type of process we have going on here, perhaps to not quite the same extent, but it is similar in the overall impact. More light, or more color equals better visual acuity, and that's the big advantage in working with LEDs. And the 4100K color temperature ties us back into what's been everyone has been familiar with in the outdoor illumination field for years. Now, we take great pride in the fact that we protect our system completely. We have taken and we've got these prisms in here that now have better light output passing through them. We have a higher output LED. We take the entire system and we put it behind glass to create an IP67 rated module that operates for the VLED system. But there is a drawback to it. By putting the light behind glass, we are losing some illumination because of two things. One has to do with what's called interreflection, or light bouncing off of glass as the angle steepens. The other is absorption, which is transmission through the glass. It all adds up, it all adds up to the fact that on a typical glass lens, from nadir to 75-degree angle out, you can have nearly a 40% loss of intensity of your light source because of these two elements. Well, with LEDs, we're already starting off with a low enough light level. We don't need to reduce it anymore. So what we've done here now is this is the third improvement we've made in the VLED optical modules, is that we've now developed worked with a manufacturer of architectural glass to develop an anti-reflective coating that goes on both the inside and the outside of the lens that restores, both through transmission and reflective properties, about 9 to 12% of the light passing through the lens, which gets our numbers up a little bit there as well. So we have an improved LED, we have an improved prism reflector that's putting more light out, and we have a lens now that's allowing more light to pass. All these things go together to produce a far better system. And that system then relies on what the last major technical point is. The most important point in any type of LED system is addressing heat, the killer of LEDs. Now, heat kills any kind of electronic component, but with LEDs it does it in two ways. One, it not only can damage the component and burn it out prematurely, but the more heat that is applied to an LED, the less light comes out of the LED, the less life expectancy you get out of the LED. And there's a number of things that can be done to mitigate this. One of the things that can be done is to just reduce the amount of heat that's being produced by the system. We have to understand where that comes from. So we're not going to take you through an electronics class here, but we're going to give you a real quick, simple basic on an LED, or diodes in general. A diode is made up of usually silicone material, half of which has been doped with material such as arsenic, which gives it a negative influence, and the other half doped with material such as boron. It can be something else. It can be phosphor, that will then give it a positive leaning, a positive influence. And the reason we refer to it like that is that you don't really add protons to it. You either add electrons or take electrons away. If I add electrons by doping it with arsenic, and if I go to the other side and take electrons away by doping it with boron, I create either a negative or positive impact. And where I combine those two components together, elements together, the electrons combine with the holes, or the positive elements that are there, and they create what's called a depletion zone that doesn't allow current to pass through the LED in one direction or another. Now, if I reverse bias it or put the power to it the wrong way, it'll never have power pass through it. But if I put power to it the correct way, and that power that's needed is what's called the forward voltage, I then get a movement of electrons from that negative side to the positive side. Now, notice what happened there again. As I apply power to it, electrons move. When some of them move, they create those funny little yellow arrows and others don't. Well, that yellow arrow represents the release of energy in the form of a photon, and in an LED, that's how we produce light. Some of the electrons move and recombine, but don't produce light. And that's the game of the chip manufacturers, to make the LEDs better at getting every electron as it moves to release energy in the form of a photon. That's their job. But there's things that we can do from the manufacturing level to help that process along. And one of those things that we can do is to understand the impact of drive current on the lumen output of the system. As we increase the drive current, we reduce the number of LEDs that recombine on the other side of the component and release photons. This is a chart that's taken directly from the VLED's Rebel ES pamphlet or technical sheet, data sheet. And you can pick this up online and then look for it. It's on about page 12 out of 30-some pages for the Rebel ES. You'll notice on the very first line here, this is the LED we use. It's a 4100K neutral white LED. 350 milliamps is our preferred drive current. Produces 130 lumens. Notice here, here's a 5600 that produces 135 lumens. Notice also that the 3000K only produces about 81. This is the reason that we can't really push down to those warmer colors at present, because they're not as efficacious. But let's stick with this top line here. We've got 130 lumens at 350 milliamps, 230 lumens at 700, 310 at 1,000 milliamps or 1 amp. If we chart this out, what it's telling us is we have somewhere in the neighborhood of approximately a 5 to 6% loss for every 250 to 300 milliamps, or every 175 milliamps we're adding to the system here. So when I go from 350 milliamps to 5.25, I do increase my lumen output, but at a 6% loss of efficiency. If I step from 525 up to 700, I go from 183 to 230, which is about 11.5 to 12% loss from the initial 350 milliamps. So they become less efficacious because you're having fewer electrons emit photons as we increase the current, the drive current. Something else, though, happens. In physics, when you create 1 watt of energy, you also create 3.41 BTUs of heat. They are directly related to each other. And when we look at the way this system operates, whether or not my electrons produce light, they're moving, and so they do absorb power. So when I go from 350 milliamps, for example, to 700 milliamps, I get 77% more lumens, but I produce 100% more heat. And heat does 2 things. 1, it reduces the overall life of the LED. In this case, it cuts it down by at least half, if not more. 2, it reduces the light output of the LED. So not only have it become less efficacious just in general because I don't have as many electrons recombining, I become even less efficacious because the heat reduces the output of the LED. This is the reason why we've elected to stay at 350 milliamps as the prime drive current for all of our systems. Put it within a sealed system that keeps it clean for the 120 to 140,000 hours. We give you a discrete module that fits a variety of luminaires, seal it to this IP67 rating, give you independent control of each LED. No other system has all of these features added to it with the advancements on the lens and everything else. And then we can take that module and put it inside of any of the luminaires we have and not worry about that module overheating and losing the life expectancy or the light output. Now, we still have to go back and, for purposes of the LM80 tests, provide heat tests for all these fixtures, which we do have for you, so we can tell you what the life expectancy and light output would be of the module versus in an aerolume versus a tsunami, etc. But we're the only ones who do it like this. Because when you look at the other systems out there, In order to save costs, they pack more and more LEDs into their systems, and then they do things like this. They put airflow screens in their fixtures and heat sinks, or airflow screens where birds can nest and block the flow, which compromises the life expectancy. You notice the theme here? Every one of these systems has either exposed the cooling fins or have these airflow screens that allow airflow through the systems because they haven't been engineered to conduct and convect the heat away from the components efficiently by themselves. I think this is probably the most interesting one here. Here we've got cooling fins and an airflow screen, but notice the last sentence here says, depending on mounting orientation and accessories, the luminaire is UL and CUL listed for wet locations. This definitely is not sealed to an IP67 rating. The last element here that helps us understand this issue of heat, it comes down on a very, very close and controlled level. And you think I'm going to go into the weeds here, but we're almost done. We have like 2 more slides to do here. What we're showing you is the LED that we showed you earlier, and we're showing you a schematic drawing of it up above and on the side here from a top view and a side view. The heat measurement that we do is taken right on the component board itself, and this is the suggestion of LumaLEDs. They tell us that if we take a heat measurement reading on that little tab on there, we know that that temperature is about 13 to 15 degrees C difference between that tab and the LED itself on the inside of the LED. And in our own testing, we also know that from that little measurement point, that thermocouple test point, to our heat sinks on the back of the module, there's about a 3 degrees C or about a 6 degree Fahrenheit difference between those points. So we can tell exactly what the heat is at the junction of in the LED, which allows us to control and monitor the life expectancy and the light output of the unit. Not everybody does this. Here's an interesting example. Now, this is a study that was done by a university on a system that's made by a company called EcoFit that looks very similar to ours. It's a cast module with fins and a sealed system, but notice where they have the heat module, the heat sensor. It's located approximately 1/4 of an inch away from the LED itself. Now, we can tell you for sure that there's going to be more than a 15 degree C difference between that measurement point and the LED. It's not going to be like it is over here on the circuit board in our case. And the reason this is important is follows. This is the heat study that they did on their unit. And we're going to show you a comparison of a 350 milliamp to a 525 milliamp system, the impact heat has on light output. First of all, let's take a look at this 63 LED 350 milliamp system. At 25 degrees C, or approximately 77 degrees Fahrenheit, we're producing a temperature on the LED, that little point that we showed you there, of 141 degrees. Now, we know it's probably hotter than that, but that's the temperatures on there, and that results in a 4% reduction of light. If we move that temperature up 10 degrees C from 25 to 35, or from about 77, 78 degrees to about 96 degrees, we increase the temperature on the LED by 16 to 17 degrees and lose almost twice the amount of light. Now, let's say that instead of doing that, I go back to the ambient temperature of 77 degrees or 25 degrees C, but I operate the system at 525 milliamps. Well, remember, wattage equals heat. So if I increase the current, I'm increasing the wattage, I'm increasing the heat. So on this 25 degrees C ambient temperature, instead of being 140 degrees Fahrenheit, the system now operates at 168 degrees almost, which is a loss of almost twice as much, 9 to 10%. When I then push that all the way up to the 35 degrees C or 95 degrees Fahrenheit, I'm running that component at almost 185 degrees, 186 degrees Fahrenheit with a commensurate loss of power. So not only did I lose approximately 6 or 7% because of the higher drive current, I'm losing another anywhere from 10 to 15% because of the additional heat. So the question is, why would I operate it at a higher current rating? I can already get out of the system as it is the light that I need. So if I compare the 525 milliamp system from EcoFit to the 350 milliamp system that we produce, you can see that the patterns here for a type 2 are virtually identical to each other, but we're doing it for considerably lower power consumption, for considerably lower heat generation, and therefore considerably longer life expectancy on the LED. Friends, we've studied this thing from every angle we can. We've looked at it and we've said, you've got to make your choice up for yourself by knowing all the facts about the system, but it requires knowing the facts about LEDs. Unfortunately, probably, bad way to word it, but unfortunately today, we're not selling just lamps and reflectors anymore. Fixture sales are becoming very much the same as control system sales. The technical aspect of them is great, and we want you to have the comfort and reliability to know that at U.S. Architectural and Sun Valley Lighting, we've got that technical prowess and understanding to be able to develop for you the best optical systems that are out there on the market and using the latest technology that's out there on the marketplace today. Don't be afraid to go out there and sell it. Don't be afraid to go out there and promote it, because it is technically the most advanced system out there and will not leave you short. And yes, we absolutely believe we are the best at this. And we're going to prove it to you even more next week, because we're going to present yet another new product to you based on LEDs. I want to thank you for your attendance to this session and for hanging in there. All the credit in the world to you. Hope I didn't put you to sleep. Too bad. I wish I had an air horn so I could wake you up right now. But this brings the conclusion to our presentation. If you have any questions, feel free to go ahead and email them to us. If you want a copy of that cutoff report or that information concerning HID versus LED and the measurement of cutoff, go ahead and shoot an email to myself or Don or Mike. We all have a copy of it, and we'll send that out to you. I want to thank you again for your participation. Take care.